In this video, we're going to take a look at ramps. And ramps are oftentimes in physics called inclined planes because you take a plane, like a flat board, and you lift it up so that it makes an angle with respect to a horizontal line. Now, inclined plane problems really, at their heart, are not any different than solving some other two-dimensional force problem. They're virtually identical. However, the one thing that you need to keep in mind that I'm going to bring up here, and we're going to see it in another type of force problem in a little bit, in a couple videos. And the idea is that you want to make sure that you align an axis with the acceleration. I'm going to do some examples where the object is accelerating, one where the object is not. And then hopefully that makes it more clear. But you should be able to see here that if this block is going to accelerate down this ramp, then the acceleration is not in the x dimension, it's not in the y dimension, but the acceleration exists both in the x and y dimension. And that kind of, you can do it that way. There's absolutely nothing wrong with doing it. But by doing that, you have to work a more difficult problem. And I'm going to have more to say about this in just a couple of minutes after we revisit the geometry of doing a ramp problem and how we come up with some of the quantities that we do. But the first big idea, you want to make sure that either your x-axis or y-axis is parallel to the acceleration. We have a ramp. These ramps always make an angle with respect to the horizontal, unless they give you a diagram and they show you an angle up here in the corner. And why they would be doing that, I don't know, but you never know. It's just how they mix things up and make sure that you're exercising all of your skills. And if we have a block on the ramp and this block is on a frictionless ramp, just to keep it simple, then that means we have a normal force, which by definition points perpendicular to the surface of the ramp, and then the only other force which can exist is the force of gravity, which is straight down, and that points towards the center of the earth. Okay, so when looking at this problem, the first thing we have to do is change our axis so that the x-axis, the new x-axis, would be parallel to the acceleration. And so we have this normal xy coordinate system here. This is y and here is x. But what we're going to do is we're going to take that coordinate system and we're going to rotate it so that, I'll do this in white, so that our y-axis is now perpendicular to the ramp and our x-axis is parallel to the ramp. So this becomes, I'll call it y prime, and this becomes x prime, where the prime just means this is our new axis in Cartesian coordinates. So I guess the big point is Cartesian coordinates, while we tend to think of them as being absolute in a horizontal and vertical orientation, that does not have to be the case. And this really goes back to the idea that I've been saying since the very beginning. You get to choose your coordinate system. In this case, we choose to make our coordinate system so that it's parallel and perpendicular to the ramp. And that just has a practical reasoning behind it, a practical purpose, which I'll explain again in a couple minutes. If you chose to use spherical coordinates or polar coordinates to try to solve, these problems, to set them up, you can do that. There's no rule that is stopping you from doing that. It just gets to be a little bit trickier when you do it. Okay, so now that we have our ramp in our new XY coordinate system, we can see that the normal force is parallel to the y-axis, but the force of gravity has two components in the new coordinate system. And gravity is going to have a component which is perpendicular to the ramp, and then a component which is parallel to the ramp. So I'll refer to this as FG perpendicular and then FG parallel. Now, you may still choose to call it X for the parallel and Y for the perpendicular. I will pretty much always say perpendicular and parallel so that it's clear it's relative to the ramp and not a horizontal and vertical line. But there's nothing wrong or inappropriate with saying X and Y. So whenever we solve our problems, remember we set up Newton's second law. We have F net X is equal to MAX, and then in the Y dimension we get F net Y is equal to MAY. And so all we're seeking to do is help eliminate some of these terms by rotating the coordinate system. So in the X dimension we do have an acceleration, but in the Y dimension there is zero acceleration. Because remember, we're looking now at parallel and perpendicular. And because the block is not accelerating perpendicular to the ramp, we can say that it has zero acceleration. In that dimension, it is in equilibrium. Now, when I was in college, the professor just said that this angle here was the angle theta and really didn't offer much of an explanation why. And then he also went on to say that you can do it using the regular Cartesian coordinate system if you so desire. And so I set out to do that one day because I was very uncomfortable with this notion. I didn't understand where it came from because it wasn't carefully explained to me, and I wasn't the most astute of students. I just kind of went to class, tell me what I need to know, and I didn't really do enough of my own personal study. So I sat down one afternoon, just kind of preparing for school, and decided, you know what, I'm more comfortable doing it the other way, so let me try it that way. And I don't know, it probably took me a half hour, 45 minutes to get through a problem, and the end result is that I ended up with exactly the same thing that we're about to get. And it took me a lot more brain power to figure it out. So it's real easy to understand where this angle theta comes from, how we know that that is the angle theta. So first things first, and that is that the bottom of the ramp is parallel to the earth, so the force of gravity is perpendicular to the bottom of the ramp. So that's a 90-degree angle. Now a triangle, the interior angles add up to 180 degrees. So I've got theta, I've got 90, and we'll just call this angle in here beta. We've seen this before, it's just a review. Okay, and so what we get is 180 degrees is equal to theta plus beta plus 90. Now, we also know that a straight line is equal to 180 degrees. So the straight line is going to also be equal to theta plus beta plus 90. So here's our straight line, right? It's the ramp itself. And we know that this is 90 because it's the perpendicular component. This is beta. That was understood from our original triangle. And so when we're asking ourselves, what is this angle in here? Well, it must be theta because we already have beta and we already have 90. So that's how we know that this is the angle theta. Now, at this point, how do you get FG perpendicular and FG parallel? Well, it's just going to be your basic trig identities, right? That is that we're looking at, for the perpendicular component, this one right here, this is the side adjacent to my angle. Okay, so I would just write FG perpendicular is equal to FG cosine of theta, and for parallel, it's going to be FG sine of theta. And this is the part that bothered me as a student, because I was in the habit, now mind you, this is not a guarantee, but I was in the habit of writing the x component is equal to something times the cosine of theta, and the y component was equal to something times the sine of theta. And that's not always true, but I always set my problems up to be that way. And so when all of a sudden I'm being told that the new y component, the perpendicular component, is cosine, it just blew my mind. and I didn't want to accept that. Okay, but it's actually, very straightforward, and there was no reason for me to have any angst at all over the situation. But students think the way they think, and so we just have to grow and mature in whatever it is that we're doing. Okay, so that's the basic idea here. We're just going to rotate our coordinate system, and by doing that, in most of our problems, that's going to make the forces always parallel to an axis with the exception of gravity. Now, don't misunderstand, there are some problems that I'm going to give you in class where you're going to have a mixture of forces that are, I'll say, anti-parallel or perpendicular, or not parallel or perpendicular, where you have to find components in addition to gravity. So, it's not an absolute rule once again. However, as a general rule, by rotating your coordinate system, you make the majority of your forces parallel and perpendicular, and so that's going to save you some work. In addition to, the acceleration can pretty much only ever be parallel to the ramp, which also saves you more work. So that's the reasoning behind our choices here. So let's take a look at our first example. Okay, now in this example we just have a 10-kilogram crate which is at rest on a rough ramp, making a small angle of 20 degrees. And we want to know what is the minimum coefficient of friction so that the crate doesn't slide down the ramp. So we're going to start by drawing a diagram. Here's our ramp. It's going to make an angle of 20 degrees. We put a crate on that ramp right here. And now we draw our FBD. Now the FBD, please keep in mind, is not generally drawn on the picture, but I'm going to put it on the picture for simplicity. And so we have the normal force points perpendicular to the ramp, force of gravity is straight down, and there's one more force because we know friction is involved. They ask about the coefficient of friction. The friction force is going to be pointing up the ramp. Now remember, that's opposite the slide. Okay, the force of gravity is pulling downwards parallel to the ramp, FG parallel, and it's friction which is offsetting FG parallel. So if we draw a working FBD, it would look something like this. So there's our crate. We would have the normal force, the friction force, which is offsetting FG parallel, and then we have FG perpendicular. Now we're going to start this problem using the x-axis because they're asking about the coefficient of friction, and the friction force is parallel to the x-axis. So we'll start there. So we write F net is equal to ma. We know that it's not moving, so therefore the acceleration goes to 0. Now we substitute our forces into F net, and in the x dimension, the positive direction is going to be up and to the right, which is friction. The negative is gravity, so we write the force of friction minus the force of gravity parallel is equal to 0. And so now, knowing that we're looking for the coefficient of friction, right, we're looking for the coefficient, so we're going to solve for friction. So we get the force of friction is equal to FG parallel. And since I don't have numbers for FG parallel and the coefficient doesn't show up, I have to redefine my quantities. And I'm going to use my definitions from the equation sheet to do that. So FG parallel becomes FG sine of theta, and the force of friction, the definition, now this is static friction, that's going to be equal to mu sub s times the normal force. Okay, we're looking for the minimum, and so we use the limiting case where the maximum possible force has to be equal to this, and that's going to be the limiting case. All right, so we rewrite and we get mu sub s times the normal force is equal to Fg sine of theta. So now we have mu, all we have to do is solve for mu, and we get mu is equal to Fg sine of theta over the normal force. So now let's go through our checklist. Fg, do I have it? Well, no, actually I don't. What am I given? I'm given 10 kilograms, and 10 kilograms is a mass, not a weight. It's not a force. Is theta given? Yes. Is the normal force given? No. So what I have to do now is find these values. Put this equation in terms of the information which has been given. So to do that, we'll first look at gravity, because that's a pretty easy one. And we know that the force of gravity is defined by m times g, or mass times the gravitational field. But now the normal force, this one's going to be a bit trickier. The normal force is going to have to come from the y dimension, and so we'll use Newton's second law in the y dimension. And so for that we get F net is equal to ma, and in the y dimension, that's perpendicular to the ramp. We know that there's no motion, and therefore it's an equilibrium. And so we can also write the normal force minus Fg perpendicular is equal to 0. And the normal force is what we're looking for, so we solve for that, and we get Fn is equal to Fg perpendicular. Now again, if I go through a checklist, I look to see, do I have Fg perpendicular? I do not. Again, I have a mass, and so I will substitute the definition of gravity, Fg is equal to mg, in for that. And in addition, we know the perpendicular component is going to end up coming from the cosine of theta. So we rewrite our normal force function as mg, substituting mg for Fg, and then to get the perpendicular component, I write cosine of theta. So that goes back in for the normal force. And what we get is mu is equal to mg sine of theta over mg cosine of theta. And this may perhaps be surprising to you, but mg is going to cancel out, leaving us with mu is equal to sine of theta over cosine of theta. And if we put this into our calculator, make sure that we are in degrees and not radians. So what we get is the sine of 20 degrees divided by the cosine of 20 degrees. And that's going to be 0.364. All right, now there are no units associated with that answer. Okay, so let's take a look at one more example, and this one will include acceleration. Okay, so here we have a crate which is on a rough ramp, and this crate is going to accelerate down the ramp. So it's a pretty steep ramp. It makes an angle of 50 degrees, and friction is not enough to hold it back, so there it goes. Okay, so like always, the first thing we have to do is draw our FBD, and in this case we have one touch, which can provide up to two forces. So we're going to have the normal force, and then we're going to have the force of gravity. And because we're sliding on a rough ramp, we know that a friction force must exist pointing opposite the slide. So once again, we have three forces. So now we're going to work in the x dimension first because that's the dimension we're going to have an acceleration. Again, we're looking for acceleration. So we start by writing F net is equal to ma, and it is in non-equilibrium, so we keep it like this. Horizontally, or I'm sorry, parallel to the ramp, we've got a few forces, two forces. We've got friction pointing this way, and then we have FG parallel pointing that way. So we have FG minus FG parallel is equal to MA, and we need to redefine our variables in terms of what we know, and that's actually an F friction, not FG. So we redefine our variables to try to get this into terms of what we know. And we have friction is equal to mu times the normal force minus FG parallel, which is FG sine of theta, is equal to MA. FG we redefine as mg, so we get mu Fn minus mg sine of theta is equal to ma. And now we're solving for the acceleration, so we're going to leave everything like this for the moment, but we go through our checklist of what we know and don't know. So we have mu, we don't know the normal force, we have to find it. We have the mass, and we know gravity, we know theta. Okay, so we know the mass, and this is what we're looking for right here. So we're going to have to go to the other dimension in order to get the normal force. So the normal force coming from the y dimension now, we write F net is equal to ma, and perpendicular to the ramp there is no acceleration, so we're just going to end up with the normal force pointing up, and then FG perpendicular. So we get Fn minus FG perpendicular is equal to 0. Solving for Fn, which is what we need to solve this problem, we get Fn is equal to FG perpendicular. And FG perpendicular is an unknown quantity as stated, but we do know that FG perpendicular is equal to FG times the cosine of theta. So we'll put that back into our equation, and we get Fn is equal to FG cosine of theta. So now rewriting everything, we get mu times FG cosine of theta minus mg sine of theta is equal to ma. And once again, we have to rewrite FG with an mg, so we get mu mg cosine of theta minus mg sine theta is equal to ma. We get to cancel out the m's. And to simplify the math here a little bit, we'll write this as g times mu cosine theta minus sine theta is equal to the acceleration for the block going down the ramp. So we know g, we know mu, we know theta. So now all we have to do is solve. So we'll get out our calculator here, and we get 9.8 times mu, which was 0.25, times the cosine of 50 degrees minus the sine of 50 degrees. And the acceleration is minus 5.93. meters per second squared. So anytime you solve a problem and get a numerical answer, you should always double check to make sure that the answer at least seems reasonable. So the first thing that you're going to see about this answer is that we have a negative sign. So does it make sense for the acceleration to be negative? And the answer to that is yes. That's because the block is moving towards the left, which is the negative direction. So that's good. And we have a value here. The magnitude of our acceleration is less than 9.8. It's approximately it's a little more than half, probably closer to 2/3. But again, that also makes sense because that's a very steep ramp. So we can have some measure of confidence that we have the correct answer.